Hello everyone, my name is Dr. Raj Dandekar. I graduated with a PhD in machine learning from MIT in 2022, and I am the creator of the Build DeepSeek from Scratch series. Before we get started, I want to introduce all of you to our sponsor and our partner for this series, invideoAI. All of you know how much we value foundational content, building AI models from the nuts and bolts. InVideo AI follows a very similar principle and philosophy to that of us. Let me show you how. So here's the website of InVideo AI. With a small engineering team, they have built an incredible product in which you can create high quality AI videos from just text prompts. So as you can see here, I've mentioned a text prompt, create a hyper realistic video commercial of a premium luxury watch and make it cinematic. With that, I click on generate a video. Within some time, I am presented with this incredible video, which is highly realistic. What fascinates me about this video is its attention to detail. Look at this. The quality and the texture is just incredible. And all of this has been created from a single text prompt. That's the power of NVIDIA's product. The backbone behind the awesome video which you just saw is NVIDIA AI's video creation pipeline, in which they are rethinking video generation and editing from the first principles. To experiment and tinker with foundational models, they have one of the largest clusters of H100s and H200s in India and are also experimenting with B200s. InVideo AI is the fastest growing AI startup in India, building for the world. And that's why I resonate with them so much. The good news is that they have multiple job openings at the moment. You can join their amazing team. I am posting more details in the description below. Hello, everyone, and welcome to the next lecture in the Build DeepSeek from Scratch series. Today, we are going to learn about a very important concept, and that is the need for an attention mechanism. First, let me quickly summarize what all we have covered so far in this lecture series, and then let's come to the topic of discussion today. So, two lectures back in the lecture called DeepSeek Basics, we looked at the four phases of the DeepSeek architecture, or rather, the four phases through which we are going to cover this lecture series. The first phase is the innovations in the DeepSeek architecture. The second phase is the training methodology. The third phase is the GPU optimization tricks. And the fourth phase is the model ecosystem. In the previous lecture, which was titled LLM architecture, we started looking at phase 1. In particular, our main goal is that in the next two lectures or 2 to 3 lectures, we have to start understanding about the multi-head latent attention, which is the first major innovation in the DeepSeek architecture. However, to understand MLA or multi-head latent attention, we cannot directly start looking at that concept. We need to slowly work our way towards it. So first, we looked at the architecture of the LLM itself. We saw that the architecture of the LLMs looked something like this. We had three sections. First, we had the input section, then we had the processor, and then we had the output section. Each section essentially had different building blocks. So we saw that to really understand how the, if you think of the LLM as the engine, right? And to truly understand how the engine works, we really need to open the engine and try to see what lies underneath. And how does essentially LLMs learn to predict the next token or the next word? If you think of this analogy as similar to the motion of a car, we see that if you put fuel in the car essentially moves, right? So something happens in the engine and the car moves. Similarly, for LLM, the fuel is the sequence of words which you feed in as an input to the engine, which is the LLM, and the output is the next word prediction or the next token prediction. And that's why we also called LLMs as next token prediction engine. Now, this engine has huge number of parameters. GPT-3 has 175 billion, GPT-4 probably has around 1 trillion, and GPT 4.5, which was released recently, probably has around 5 to 10 trillion. So, to truly understand how this engine works, we opened the black box and we looked at these three aspects. But I did not directly explain these three aspects to you. I told you that what if you put yourself in the shoes of a token or a word and you imagine yourself going through the different phases. So, if you are a token, first you get assigned a token ID, that's your badge. Then you get assigned a token embedding vector. Then you get assigned a position embedding vector. The token and the position embedding are added together, and that's the input embedding, which is your uniform. Now, similarly, whoever are your neighbors, they also have their uniform or the input embedding, and all of you together onboard the train to the transformer. Each transformer block has multiple components such as the normalization, multi-head attention, dropout, skip connection, again a normalization layer, a feed forward neural network, and a dropout layer followed by another skip connection. This is just one transformer block. There are multiple transformer blocks like this. It can be 12, 24, 96, etc. So as a token with your uniform, which is your input embedding, you have to go through all of these transformer blocks. And then when you come out, you have a layer of normalization. And finally, you have an output layer in which if you are a 768 dimensional vector, you are mapped or up projected into a 50,000 dimensional vector. Why 50,000? Because that's the vocabulary size, and that essentially helps us to choose the next token. That's the whole life cycle of a token as it goes through the LLM architecture, right? In today's lecture, we are going to focus on one single aspect of this entire architecture, and that's this multi-head attention. I want you to appreciate where this multi-head attention comes into the picture. So, out of all of these steps which the token goes through, the multi-head attention comes in the transformer block, and within the transformer block also it comes after the normalization layer in this particular case. So today we are going to understand uh, multi-head attention, but to do that, first we will understand what is attention itself and what is the need for the attention mechanism. Why do we start talking about this term attention? Why has it got so much popularity in recent times? So, our today's goal is to motivate the concept of self attention. We are not going to see the mathematics of self attention mechanism today. Today, the whole goal is to try to understand why we need attention in the first place and why it has been such a game changer for large language models. Just think about this, right? Out of all of these steps which a token goes through, the most important step lies within the transformer block, lies within one step of the transformer block, and that's the attention. That's why I've marked it with a different color here. This block of the train essentially gives all the properties which have made LLMs so good at understanding language. So, to truly understand how attention works, I have created this separate lecture for you in which we'll try to motivate the need for an attention mechanism. Before understanding why we needed attention and how it has changed the field, first let us deep dive a bit into the field of generative AI itself. So let's rewind and go back to history a bit. I believe it is essential to appreciate the attention mechanism. In 1960s, there was this Eliza chatbot. You can think of this. I would not call it a large language model. I would call it a chatbot. It was the first natural language processing chatbot, which was meant to be a therapist. So, if you ask, please tell me what's been bothering you, I can say that I am having a hard time learning AI. Can you help me? You believe it is normal to be having a hard time learning AI? So see, it's like not very helpful, but remember that it's 1960s. So at that time, this was considered to be a revolution. So here you can see the original program was described by Joseph Weizenbaum in 1966. Compare this to ChatGPT right now, where we say that I want to learn about AI. Can you help me, and let me switch the model to GPT-4o so that I get a quicker response. And then here you will see that I am immediately presented with a list of actionable items which I can start implementing to learn about AI. So within a span of 64 years, we have come a long way in the field of natural language processing and understanding language itself. So let's see what happened between 1960s to 2020s, right? So 1960s is where the ELISA chatbot came out. Then in 1980s and 1997, there were these two major fundamental building blocks of the field of generative AI or language modeling, and you can think of those as recurrent neural networks, which came out in 1980s, and long short-term memory networks, which essentially came out in 1997. Both of these built on top of the neural network boom, which happened in the 1970s. So people discovered that neural networks can do a bunch of awesome things. But the real issue which neural networks have is that neural networks essentially neural networks can't deal with memory. And that's the biggest issue with neural networks. Why do you have to deal with memory? Because imagine that if you're predicting the next word, right? Or if you're generating some new text, you would want to know what has come at the start of a paragraph. Just having a small memory does not help. Context is very important. And this word will come up a lot in today's lecture, context. Context essentially means that if there is a huge paragraph uh, being given to the model, and we want the model to do some task or just answer some question, just looking at the sentence, the word or the sentences which come immediately does not help. We need to have a context in mind of what was being told at the beginning of the paragraph itself, right? So if I say that, let's say, I am from Pune, India, okay, and then after that, let's say I write a huge bunch of different things, I write a huge bunch of sentences, and then finally I ask, what language do I speak? Now, to generate a response based on this question which has been asked, all these things in the middle are not very important. But I need to have a context of what came at the beginning of this paragraph, because that's what will help me really answer this question. That's why you need to have memory. And neural networks had no provision to encode memory really. But recurrent neural networks and long short term networks solved that problem. Let me quickly show you how they solved that problem. So, people typically used RNNs or LSTMs initially for sequence to sequence modeling, or what is called as sequence to sequence translation tasks. So, simple sequence to sequence translation tasks can be just language translation. If you want to take a bunch of words, right, and if you want to translate those from one language to another language, you can use a recurrent neural network. So recurrent neural network has a bunch of hidden states like this: H0, H1, H2, H3. Let's say these are the input words. I will eat, right? And I want to translate it to French, which translates to je vais mange, which has been written over here. The way I can use a recurrent neural network to do this translation is that I have an encoder block and I have a decoder block. Both these encoder and decoder blocks have something called as hidden states, which you can think of as vectors or matrices. So here's the hidden state H1, hidden state H2, hidden state H3 of the encoder. And then we have the hidden state S1, hidden state S2, and the hidden state S3 of the decoder. Let's visualize what happens in the encoder block. In the encoder block, you first give the first word of the input sentence, which is I. That gets converted to the first hidden state H1. Then you give the second word. Now keep in mind, to get the second hidden state H2, you use the second input, but you also use the previous hidden state. That's how memory is captured in recurrent neural networks. The previous hidden state is used to compute the current hidden state. Similarly, when you come to eat, that's the input x3, but to compute h3, which is the final hidden state, you use the previous hidden state, which is h2. and H2 encoded H1, or H2 had the knowledge of H1. So H3 now has the knowledge of H1 as well as H2. H3 has the knowledge of the past, it retains memory. So H3 can be thought of as that one vector, maybe it's like a 500 or a 1000 dimensional vector, which essentially contains all the information of what the input essentially means. And this is the only high dimensional vector which is passed to the decoder. The decoder then takes a look at this vector, and then every hidden state of the decoder starts decoding it. So the decoder, imagine you are the decoder, right? And it's the relay race. So let's think of it as a relay race. The baton is at with H1, it passes it to H2, the H2 passes it to H3. Now H3 has the baton which passes it to the decoder. Now I'm the first hidden state of the decoder. I have the baton. I decode the first token, which is Joe. Then I pass it to the second. Then I decode the second token, and then I decode the third token. This is how language to language translation works in recurrent neural networks. LSTMs are a bit different. To predict the current hidden state based on the previous hidden state, they also maintain something called as a cell state. So LSTMs have a provision for taking into account long memories as well as short memories. So that's essentially to increase the context window they deal with. But the architecture fundamentally remains the same. It's just that the mathematics beneath is a lot more complicated for LSTMs. Now, do you see a problem with this? Take take a look at this example which we had for discussing about context, right? What is the problem with recurrent neural networks when, let's say, you have big paragraphs to deal with? Let's say you have a big paragraph and you want to translate that entire paragraph. What is the problem with recurrent neural networks in doing that? So let's take a simple example so that I can explain that problem to you a bit better. Imagine that you have this paragraph, okay? I have constructed this randomly from ChatGPT. I want you to do the following. I want you to first read this paragraph once, maybe take 30 seconds or 1 minute or more to read this paragraph just once. Then close your eyes and then translate it into any language you want. You can translate it into Hindi, Spanish, French, German, whatever language you speak other than English. So close your eyes and translate it into another language. Were you able to do this? It's impossible, right? Because when you close your eyes, you essentially probably remember some summary of what you have read. You don't remember exactly each and every word. But to translate, we have to look at each and every word and translate it individually, right? That's the exact same problem which is happening with recurrent neural networks. Why? Because we are relying on only one hidden state or one vector to capture all the context of what has happened in the past. So it's like closing your eyes and then trying to remember the entire paragraph. There is so much pressure on this one hidden state or this vector to recollect all the memory, that if it's a huge paragraph, how can you compress all of that information in a 500 dimensional vector or a 1000 dimensional vector? Naturally, some information is going to get lost. And remember, the decoder does not take input from the first hidden state or the second hidden state. It only takes the final hidden state as the input. That's where the main issue arises. The context which goes from the encoder to the decoder is only from the final hidden state. That is why this is called as the context bottleneck problem. The final hidden state is like you when you closed your eyes and when you tried to memorize the entire paragraph. It's impossible to do that. You cannot put so much pressure on one vector. So, context bottleneck in recurrent neural networks is really not good for retaining a long range context. And this serves as a great pathway for understanding why attention comes into the picture. So, now if you look at the recurrent neural network, let me rub some things over here or erase some things. What do you think is the ideal solution to this problem? If, let's say, this is the problem which we are encountering, right? All the context cannot be captured in one single vector. What is the solution to this problem? Well, the solution seems to be that, let's say, when we are decoding, when I'm decoding this, let's say when I'm decoding from the first hidden state of the decoder, instead of having access to just the final hidden state, what if I have access to all the hidden states of the encoder? and all the inputs also. So if during decoding I have access to all of the inputs, and then I can make predictions such that, okay, if I'm decoding the first token, I should give more importance to the first hidden state, and I should not give importance to the second hidden state, and I should not give importance to the third hidden state. What if I could create a mechanism which can understand the relative importance which needs to be given to different tokens? This is the most important part of this lecture, so please try to focus over here. The main thing which can solve the context bottleneck problem is that when I'm decoding, what if I develop a mechanism which can try to quantify how much importance I should give to every hidden state? So while the first decoding is taking place, let's say I give 80% importance to the first hidden state, 10% importance to the second hidden state, and 10% importance to the third hidden state. If I have this information along with me, then the context bottleneck problem is solved, right? Because even if the paragraph is long, if I can attend to all the tokens in that paragraph, I can essentially also give importance to something which has come in the past. So let's say if this is the sentence and I'm predicting something here, in the attention mechanism I can just try to see how much attention to give to the first token, the second token, third, and the entire paragraph, and then I can say that I need to give maximum attention to these tokens over here. So you see, I'm already starting to use the word attention over here. You can think of it as relative importance to individual tokens in the paragraph. So the ideal solution is that we need to selectively access parts of the input sequence during decoding. So when you are decoding, let's say, I want to make certain predictions so that if I'm decoding the first token, right? This alpha 1 1 is the relative importance given to the first hidden state. Alpha 2 1 is the relative importance given to the second hidden state. Alpha 3 1 is the relative importance which is given to the third hidden state. So I want to be able to make predictions such that alpha 1 1 is 100%, alpha 2 1 is 0, and alpha 3 1 is 0, something like that. But you see here, instead of just relying on H3, I'm now relying on all of my previous hidden states, and not just that, I'm quantifying how much I should rely on each of the previous hidden states. So again, this is important. We need to selectively access parts of the input sequence during decoding, and I want to explain this to you with this example again. Let's say I take a screenshot here, okay, and then I put it over here. Let's try to understand what this statement actually means. So, if I ask you to translate this paragraph, how would you actually do it? You would probably start. You would actually probably start with, let's say, this, right? Let's say you start with this. That how much words you can look at one point. Let's say that's your context window. You cannot look at more words than this at one point. Then what your mind will do is that, for your mind, the rest of what comes in the paragraph is irrelevant, right? So you will mask out all of that. In your mind you will mask out all of that, it's not relevant. So what you will do is that all of these other things are not important to you now. You just want to look at the current context, and you want to selectively hide out every other thing, right? So what your mind does is that your mind pays attention. This is very important. Your mind is paying attention to this part of the paragraph, and then it's starting to translate only this part of the paragraph. And after this is translated, then your mind will move to the next, maybe next 5 words. After this is translated, your mind will move to the next 5 words, and then you will go to the next 5 words, etc. So you see what you're doing here. At a particular time, your mind is making a decision that I want to pay the maximum attention to these tokens when you're looking at the first context window, and then your mind is also making certain quantitative judgments that don't pay any attention to the rest of the tokens at all. Don't pay any attention to these. So that's what is actually meant by selectively access parts of the input sequence during decoding, right? selectively accessing parts of the input sequence. That's the most important sentence to understand the attention mechanism. It means that only pay attention to that part of the input sequence which is important at that moment. And this seems like an intuitive thing to do, right? But it's actually the most important thing which helped language models to become better. So imagine that you want to find a spelling mistake in a piece of paragraph, right? What do? You want to find out where the spelling mistake is. You go through the paragraph step by step. So you pay attention at one, then you pay attention to the next, etc. This is what LLMs also need to do. They need to selectively pay attention to the part of the sequence and then find that part, let's say, which has the spelling mistake, for example, right? So this is the main purpose of why we need attention. While decoding, we can quantify how much importance or attention needs to be given to each input token. That is what I'm getting at the moment. Now, the first paper which really implemented this was not the attention is all you need. So, if you see this paper has around 170,000 citations, right? Huge number of citations. So many people actually believe that um, the attention mechanism was first introduced in this paper, but the first paper which actually introduced the attention mechanism is this Bahdanov attention mechanism. So if you search Bahdanov attention and you click on this, you will see that this is the first paper which actually implemented the attention mechanism for translation tasks. This paper, I think, came out in 2014 and this was published at ICLR in 2015. Their main purpose was they essentially implemented this architecture in which we can selectively decide how much attention to pay to each hidden state. So that's what's called A1, A2, A3. That's the attention score. And based on that, you can do the translation tasks. And they essentially proved that we can do sequence to sequence translation in a much better manner if we use the attention mechanism. So just keep this particular paper in mind. So here you can see that on this here we have the English sentences, and on the y-axis we have the French translation, and the diagonals are essentially showing the English word paying the most attention to the translated French word. And what's cool thing about this is that the order is not the same. So the agreement on the European Economic Area, right? European Economic Area, that's English, but the way it translates to French is Economic European, right? So it translates to Area Economic European. So it's not direct word to word translation. And still, the attention mechanism essentially figures out that, see, this is the maximum, this is brightest, right? Which means the European year in French corresponds to the European year in English, although they both don't occur at the same position. So the European in English occurs at position number 5, and the European in French occurs at position number 7. So all the brightest areas are not on the diagonal. There are some which are off the diagonal itself, and even that is captured by the attention mechanism. So the coolest thing about this plot is that this off diagonal elements, because translation does not always happen word by word, right? There are some words which come before in some languages, which come after in some other languages, based on how nouns, verbs, etc. are arranged. So that's the cool thing about this paper. This was the first one where the attention mechanism was used for translation tasks. Um, and then attention is all you need paper is where the transformer block was introduced and the attention mechanism was integrated within the transformer block. That's the main advantage, or that's the main unique point of this paper. Attention is all you need. Right. So what happened is that RNNs and LSTMs are quite good for language translation, but they have this context bottleneck problem. So researchers figured out that RNN architectures are not really needed for building deep neural networks. So 2014 is where the Bahdanov attention mechanism was introduced, where they had the RNN, so they retained the RNN, plus they had the attention mechanism. So essentially in Bahdanov attention, you can think of the encoder decoder block in a similar manner, but just they added this attention mechanism. 3 years later, which means in 2017, researchers essentially figured out that RNN architectures are not even needed for building deep neural networks for NLP. And they proposed the transformer architecture. So think about the field which evolved in this way, right? 1980s was RNN, 1997 was LSTM, actually 1966 was ELISA. Let me write this also. Then 2014 was where the attention mechanism was introduced, but that was still attached to RNNs, the encoder decoder architecture of RNNs. 2017 is when researchers figured out that RNNs are not needed for natural language processing tasks. So RNNs were scrapped out, and then essentially the attention mechanism remained, but it was coupled with the transformer block. That's the main difference between the 2014 paper and the 2017 paper. In the 2014 paper, the RNN block was still there, but that was then removed, and then that was replaced with the transformer block or the transformer architecture in 2017. And then it led to this whole architecture, right? We now have the transformer block, and within that, we have the attention, right? So, this is the GPT architecture. This is not the architecture in the original transformer paper. The original transformer paper had an encoder as well as the decoder, whereas this architecture which I'm showing you right now only has a decoder. Don't get confused by this at the moment. The main purpose of this today's lecture is for you to understand why attention needed to be introduced in the historical perspective of natural language processing. And the main reason is that the one sentence you need to keep in mind is that we need to selectively access parts of the input sequence during decoding, and first attention was introduced in RNNs itself. Then researchers figured out that okay, let me get rid of the RNNs. Still, let me try to merge the attention mechanism somewhere, and that's when they merged it with the transformer block over here. That was in 2017. Then in 2018 is when the GPT architecture came out. So then it's the attention plus GPT. So GPT is based on this original transformer architecture, but instead of having the encoder and the decoder block, it only has the decoder block as you see over here, and it retains the attention mechanism over here. So the thing which we talked about why attention mechanism is needed, it manifests itself over here in this part of the LLM architecture. Now we are going to start looking at if you take a look at next token prediction tasks, what is self attention really, and what are context vectors, and what is the main purpose of the attention mechanism. So what is the main purpose of the self attention mechanism for next token prediction? So let's start learning about that now. Now that we have understood about the attention mechanism and the history of the attention mechanism, let's try to look at this term self attention. What does self attention actually mean? So, self attention means that it's a mechanism which allows every position in the input sequence to attend to all the positions in the same sequence. What this means is that, let's say, if I have a sentence, right? If I have a sentence such as the next day is bright. Self attention essentially means that until now, if you looked at the RNN, we saw the attention which needs to be given from the decoder to the encoder, right? So, if the first decoded word is a French word, we are basically looking between two different sequences. So, the English sequence is this, let's say the English sequence is this, I will eat, and the French sequence is this. This is the French sequence, and we are looking at, if you are doing the first decoding, how much attention should you give to the English sequence. So here the attention is between sequences, it is not within the same sequence. Self attention is on the other hand when you are predicting the next token, which is typically done for the LLM, since LLMs predict the next token, right? They are not specifically trained for translation tasks. To predict the next token, you essentially don't have different languages. You just have a bunch of data, right? So instead of having attention between two sequences, what you do is that you just take the same sentence, and let's say if you take a look at next, you try to find out, if you look at one token or one word, how much attention should I pay to all the other tokens in the sentence. That's the most important thing to understand over here. If you look at one uh, token essentially, or one word, then how important are the neighboring words to that particular token? Why is this knowledge, can you try to think why this knowledge is important for us? Why do we need to encode the knowledge of the tokens which essentially surround a given token? The reason this knowledge is important to us is because when you are predicting the next token, you essentially need information about the context of a sequence. You need information about how different words relate to each other. So, again, taking the same example, right? Let's say if I say that I am from Pune, India, I speak. Let's say if this is the sentence, right? If you look at speak, I need to know that when I look at speak, the maximum attention needs to be paid to Pune and India. Maybe all the other words are not as relevant because my dialect, what I speak, is very heavily influenced with the region which I come from. So when you look at a cloud of words, and if your transformer architecture or if your LLM engine has information about how one word relates to other words which are surrounding it, and how much importance needs to be paid to the different words surrounding it, then it just becomes very, very easy to predict the next token, right? If you look at one token. So that is the reason why um, the self attention mechanism becomes very important. If self attention mechanism was not there, you would have lost this contextual information about how other tokens relate to a given token which we have chosen. And I hope now you understand why it is called self attention. In this case, when we are looking at sequence to sequence language translation, the attention is between sequences. But self attention is when we look at one sentence itself and we look at tokens within the sentence, and we essentially see how these tokens are relating to each other, right? Okay, so let's take the same example again. The next day is bright. So the next day is bright. And remember that when these tokens go to the transformer architecture, they are now vectors, as you have seen before. They have this uniform now. Remember, every token has a uniform, which was a 768 dimensional vector here. That's the input embedding, right? So whenever I'm showing these blocks here, it essentially means a vector. So the next day is bright. These are all vectors now. For a transformer, it does not understand words, it does not understand sentences also. All it knows is that every token is a vector. So the is a vector which I'm calling x1, next is a vector which I'm calling x2, day is a vector which I'm calling x3, is a vector which I'm calling x4, bright is a vector which I'm calling x5, right? And now if I'm looking at a specific word, let's say next, as I showed over here, I want to see, if I look at this word next, how much attention should I give to all the other tokens? And this attention is given by alpha to 1, or I'm calling it a symbol alpha to 1. Why to 1? Because next is the second token, and I'm wanting to find the attention score between the second token and the first token. That's alpha to 1. This will be alpha to 2. This will be alpha to 3. Here will be alpha to 4, and here will be alpha to 5. I essentially want to find out all the attention scores if I'm looking at a particular token. So this is called as a query. The token which I'm focusing on right now, that's called as the query token. And I want to find out, if I'm looking at the query, how much attention should I give to all the other uh, tokens. These are also called as keys sometimes in the common nomenclature, right? So ultimately, what I want to do, I want to take this information. Let's say I get these attention scores. I want to somehow take all of this information and transform this vector from an input embedding vector to a context vector. Now here is very important distinction which I want to make. Currently next is a input embedding vector, right? So it contains token embedding plus positional embedding. But context vector is something very different. So if this is the input embedding vector for next, and if I plot the context vector in the same space here, so this is the context embedding vector for next. The context vector is actually much richer than the token embedding vector. Why? Because the token embedding vector or the input embedding vector contains no information of the neighboring words. But now my context vector consists of information of my neighbors also. That information is now baked into my input embedding. So if you have an input embedding, if you have the input embedding vector, which is the uniform which I talked about, right? And if you augment this input embedding vectors with context about the neighbors, we'll see how this augmentation is done. But essentially, this leads to something which is called as the context vector. So the whole goal of the attention mechanism or the self attention mechanism is to convert all the input embedding vectors to context vectors. So all of these uniforms, so we saw these uniforms, right? All tokens have a 768 dimensional uniform. When they come out of the normalization layer and when we go to the multi-head attention layer, what comes in the attention layer is an input embedding vector. What comes out of the attention layer is a context vector. So something much richer comes out after we exit the attention block. And that's why I marked it with a different color. The reason it's richer is because now it encodes information of other tokens also. So it retains context. So context vector is an enriched embedding vector. It combines information from all the other input elements. So in self attention, context vectors play a very crucial role. Their purpose is to create enriched representations of each element in an input sequence by incorporating information from all the other elements in that sequence. So this is again, keep this thing in mind that input embedding vectors only contain information about that word or that token. It might encode information about the meaning of that word and its position, but it has no clue of the neighbors. Context vector has clue about the neighbors, because neighbors are so important, right? When you look at a sentence, when you look at a paragraph, individual tokens don't mean anything. It's only how they relate with the neighbors that essentially produces the context of that paragraph. And why is this needed in LLMs? It's needed to understand the relationship and relevance of words in a sentence to each other. Actually, this is that fundamental thing which has made LLMs so much better. So if you look at these advancements in history, right? ELISA, RNN, LSTM, until your attention was not there. 2014, I believe, is a very critical point. That was 10 years back when the attention mechanism was introduced, and then people started thinking that, oh, instead of looking at words in isolation, what if I take a step back and try to see how different words essentially relate to each other? So then we are exploiting the maximum richness from text, because just like images are made up of patterns of pixels, text or paragraphs only make sense if you take a look at all the words together and how they relate to each other. So now the question is that, okay, you have an input embedding vector, uh, let's say for next, how do you convert it into a context vector? So you have an input embedding vector. How do you go from the input embedding vector to the context vector? And I want you to think about this from the first principles. Pause this video for a moment and think about this, right? You have the input embedding vector, and let's say you have these attention scores. How will you modify the input embedding vector so that somehow these attention scores are taken into account and you have a context vector? So you can pause here for a moment. First, you can try to also think about how these attention scores themselves are computed. Um, okay, so the simplest thing to do is that, let's say if you have this vector, right, and if you have all the other vectors, why don't we take a simple dot product? So you have the input embedding vector for next, you have the input embedding vector for the. Just take a dot product between these two, that will give you alpha 2 1. Just take a dot product between next and next, that will give you alpha 2 2. Then take a dot product between next and day, that will give you alpha 2 3. Then take a dot product between next and is, that will give you alpha 2 4. And next take a dot product between next and bright, that will give you alpha 2 5. And once you have all these alphas, you can simply do alpha 2 1 times x1 plus alpha 2 2 times x2 plus alpha 2 3 times x3 plus alpha 2 4 times x4 plus alpha 2 5 times x5. And why do we take a dot product here essentially? The reason you might think of a dot product is that a dot product essentially encapsulates information about whether vectors are similar or closer to each other or not, right? If you have one vector here v1 and if you have another vector here v2, the dot product between them will be higher than, let's say, v1 and v3. So if two vectors are similar, their dot products will be higher. And that's exactly what you wanted to quantify with the attention mechanism. You might think that I want to quantify whether two vectors are similar, right? So if next and the are more similar, of course they should have a higher attention score. So this calculation seems to make sense to me. I just calculate the dot products and then I just scale the different vectors with their dot products and add it up. So whatever the sum would be, that would be the context vector now for next. And similarly, I can find context vectors for all the other tokens as well. What's wrong with this approach? Why will this approach not work? Or why can't we just take simple dot products to find the attention scores? Again, you can pause here for a moment and try to think of the context which we are trying to encode. Um, I want you to think from first principles here. I'm going to reveal the answer very soon. All right, so the main answer is that let's say you consider this sentence: the dog chased the ball, but it couldn't catch it. Right? The dog chased the ball, but it couldn't catch it. And let's say I have the input embedding vector for dog as this, input embedding vector for ball as this, and input embedding vector for it as this. Okay. And if it is my query vector right now, uh, how did you decide to compute the attention score between a query vector and other vectors? You decided to take a dot product, right? This is exactly what I'm going to do. If it is my query vector, to get the attention score between it and dog, let me simply take a dot product between it and dog. And if I take a dot product, it's 0.51. If I take a simple dot product between it and ball, that is also 0.51. You see the problem here. Both the attention scores are completely identical, but that's not what I wanted. When you say but it couldn't catch it, it actually means the ball, right? The dog chased the ball but it couldn't catch it, so the second it means the ball, not the dog. So when I'm looking at it, I need to pay more attention to ball, not the dog. Let me write this with a different ink so that this is clear. I need to pay a lot more attention to ball when I'm looking at it, and not really the dog. But that's not what is happening here. If you take a simple dot product, there is no provision for me to encode the information that ball should be given more priority than dog. Both dog and ball should not be having the same attention score when we say it. Again, this example is a brilliant demonstration of why we should selectively attend to different tokens. The dog chased the ball but it couldn't catch it. The first it is the first dog. So if this was the query token, it would have attended more to dog. But now this is the query token, so it should attend more to ball. I don't want both to have the same attention score. So simple dot product cannot distinguish between subtle contextual relationships here. It doesn't consider the context of chase, couldn't catch, or linguistic nuance, such as the fact that catch is more likely to refer to a moving object, which is the ball. So the main issue is that simple dot product only measures semantic similarity, but it cannot deal with contextual issues. And many sentences might have contextual complexity like this, right? and I need to encode a mechanism so that I can capture these complexities, and I don't know what that mechanism would be. So then we use the trick which researchers have used for a long period of time now. If you don't know what the underlying relationship between things is, you just replace it with a neural network or a bunch of trainable weight matrices and let back propagation figure it out. And that's exactly what happened in the field of attention also. Researchers essentially could not figure out what that mechanism can be. So, and that's where the field of machine learning deviates or deep learning deviates from physics, right? In physics, if you were stuck with this problem, you would have spent 6 months, 1 year trying to develop a law for the underlying mechanism to capture complexities or underlying mechanism to capture the context. But in the field of deep learning, you don't do that. You say that I'll replace it with a bunch of matrices and I'll train these matrices through back propagation. So that's what researchers did, right? So they invented new matrices which are, let's say, called as the query matrix and the key matrix. What it means is that instead of just looking at the input embedding representations, what if I multiply every input embedding with a matrix? So if my query here is it, right? My query is it. I'll multiply it with something which is called as the query matrix. This can be a high dimensional matrix. For dog, so dog and ball are the keys, right? Because keys are essentially, if you have the query, keys are essentially all the other tokens which you are looking for. So that's dog and ball. So you multiply both of them with a keys matrix. Now see, the advantage here is that if a dot product cannot get the contextual relationship, you are hoping that these WQ and WK, you are not assuming these metrics as anything. You will initialize them randomly and then you will train them through back propagation. It's the same deep learning trick which researchers now have used for a very long time. If you cannot figure out the relationship yourself, you take a step back and you let neural network do its job. Instead of restraining the neural network by imposing some laws, let it figure it out itself. So you see, the advantage is now we have multiple trainable factors in our control. So if WQ is, let's say, 3 by 3 and WK is 3 by 3, right? So dog, ball, and it, these are my keys. And if these are the embeddings for these, which we saw here also, the input embeddings which we saw, and now I multiply these input embeddings with the query. I multiply these uh, I multiply these two with the keys. So I will multiply, so it will be 3 by 3 multiplied by 3 by 1. So this will be a 3 by 1 and this will also be a 3 by 1. So then the keys become zero point 0.9, zero point 0.2 and zero point 0.1 and zero point 0.1, 1.8 and zero point 0.1. You see, these values changed because I multiplied them with the keys matrix, and the query is it. So it will be multiplied with the queries matrix, so that the query for it will become zero point 0.5, zero point 0.1 and 0.5, 1.0 and zero point 0.1. And so now if you plot this in vector space, this is the query vector, this is the keys for ball, and this is the keys for dog. So now we are going from the input embedding space to a different space, which we get after multiplying with the queries and the key matrix. And now I will compute the attention scores between these vectors, not the original vectors. So now if you compute the attention score between it and the ball, you will see that it's 0.56. It and the ball is 0.96, and if you compute the attention score between it and the dog, that is 0.56. So here you see the attention score between it and ball is 0.96, which is higher than the attention score between it and dog, which is lower. So these are clearly distinct attention scores. So adding these trainable matrices has actually helped us. Why has it helped us? Because it has given a number of parameters to tune so that we can encode some complex relationships between tokens. So if you take a simple dot product, the attention scores will be identical. But if you have the query key matrix, we have not yet seen the value matrix, we'll see that in the next class. But essentially, if you just have trainable matrices, then you can have attention scores which are different because now you suddenly have more parameters to work with. So if you got confused in this part, let me repeat it once more. We started this section by thinking that if you have an input embedding vector, right, what can you do to the input embedding vector to get the context vector? So to get the context vector, we essentially need alphas. After you get the alphas, then you just have to multiply them with the input embedding vectors, and then you will get the context vector. But then the question is that how do you get the alphas between one input embedding vector and another input embedding vector? How do you get the attention scores? The simplest way is probably taking a dot product. But we saw that, let's say, if this is the sentence, right? And if it is my query, and if I want to find the attention score between this it, dog and ball, I will take a dot product between it and the ball first, which comes out to be 0.51. And I will take a dot product between it and the dog, which comes out to be again 0.51. So the attention scores comes out to be similar, but this is not what I wanted, because when I say it, I want it to be the ball. So I want the attention score between it and ball to be much higher than the attention score between it and dog. So how to do it now? Dot product clearly does not have the complexity to capture these contextual relationships. I need more parameters to work with. I need some knobs, which I don't know currently, but let neural networks or let backpropagation figure out what those knobs can be. At least let me initialize it randomly for now. And that's where these new terminologies come into the picture, right? I want to have new trainable matrices. Let me call this query matrix, and let me transform the input embeddings into another space by multiplying it with the query matrix, and the input embeddings for the keys, which are the dog and the ball, they will be multiplied with the keys matrix, and we'll transform it into another space. And then I will find the attention scores in that transformed vectors, between those transformed vectors. And now if my model learns these parameters of these matrices correctly, I can get the model to learn that the attention score between it and the ball is 0.96, which is higher than the attention score between it and the dog, which is 0.56. Don't worry about these multiplications or mathematics right now. I'll do the mathematics in detail in the next lecture. For now, just remember that we don't know how to physically capture the contextual relationship. So it's like an easy way out. It's a trick. You introduce the queries, you introduce the keys randomly. These are random trainable matrices. You initialize them randomly, and then you train them. So you might have heard of this word query keys. There is actually no proper physical reason why they are introduced. The only reason they are introduced is because humans could not figure out how to capture these attention scores themselves. The only way we know is that, okay, if we cannot figure it out, let me project my input embeddings into higher dimensions or different dimensions, or let me have few trainable parameters to work with, and then hopefully the training itself will figure it out on its own. And this trick humans have done in the field of computer vision also. If you train a CNN to distinguish between dogs and cats, you cannot write down all the features yourself. You rely on a convolutional neural network to do that. It's kind of a similar thing over here. In the next lecture, we are actually going to see how do we exactly compute the queries matrix, the keys matrix, and there is also one more matrix which is called the values matrix. How that is used in the next token prediction task, that we are going to see in the next lecture. So the next lecture is about the mathematics of self attention mechanism. What do we do with the queries matrix, key matrix, and the values matrix exactly? How do we calculate the context vectors mathematically, and from those context vectors ultimately, uh, what do we do in all these steps to get the next token prediction? So next class is pretty much going to be a deep dive into this section which we just saw, and expanding it into a full lecture of mathematics. But now in today's lecture, I just want to motivate these concepts of queries, keys, and values. Values we have not seen yet. We will see that in the next lecture. All right, everyone. So this brings us to the end of today's lecture, which you can think of as a mixture of the history of the attention mechanism plus an introduction to self attention for the next token prediction task. As a summary, remember how the attention mechanism has evolved. First, we had ELISA. ELISA was a revolution at that time, and it's pretty awesome considering it got invented in 1966. Then came recurrent neural networks and LSTMs. They had the context bottleneck issue, which means that all the context was compressed into just one hidden state. To solve that, we understood that we needed to selectively pay attention to different parts of the input sequence, and that is what is called as attention. So to encode that, we introduce something called as the attention mechanism, which computes the attention scores between the decoded output or the decoder hidden states and the input hidden states. That paper was the Badhanav attention mechanism published in 2014. That paper essentially still had RNN. So that was attention plus RNN. In 2017, there came a paper in which researchers realized that we don't even need RNNs. So they scrapped out RNNs and they came up with a new architecture called the transformer architecture, which had the attention mechanism at the heart of it. 2018, researchers modified the transformer architecture. They scrapped the encoder, kept the decoder, and had this architecture in which the attention mechanism was again at the heart of it. So this until now the attention mechanism was from one sequence to another sequence. Then when we talk about self attention, we essentially look at just one sequence because that will be used for next token prediction tasks. So in next token prediction tasks like GPT, we use self attention, where we look at one token and how it attends to its surrounding or neighboring tokens. So the token which we are looking at is called as query, and the other tokens are called as keys. And we want to find the attention score between the query vector and the keys. We realize that the main purpose of the attention mechanism is to get these attention scores and to convert it into context vector. Context vector is a more enriched version of the input embedding vector because it also contains information about how one token relates to its neighbors. To get these attention scores, the naive way or the simplest way to think about it is just to take a dot product between vectors. But we realize that that's not the best way to go about it because just taking a simple dot product can't capture subtle contextual relationships. Like we saw in this example, the dog chased the ball, but it couldn't catch it. The first it is the dog, the second it is the ball. To capture such contextual complexities, we need to add trainable weight matrices. So we need to increase the parameters so that we have different knobs to play around with. These trainable matrices are called as the query weight matrix and the key weight matrix. There is also value weight matrix which we will see in the next class. The input embedding for the all input embeddings are multiplied with the query weight matrix to get the query matrix, and also we have the keys matrix like that. So then the attention scores are not found between the input embeddings of the vector. They are found between the queries and the keys. And since we have a flexibility of so many parameters to play with, we hope that when we train the parameters, they will learn that the attention score between the second it and the ball is higher than the attention score between the second it and the dog. So it captures more contextual complexities. So addition of these trainable weight matrices captures more contextual complexities, and that's why we humans added these weight matrices and then we call them queries, keys, and values because it sounds cool, and it relates to the field of information theory. But if you look at it deeply, we cannot figure out the rule for this attention mechanism ourselves. Dot product fails, so we cannot figure out how to get these attention scores, how to compute them ourselves. So we turn to neural networks to do the job for us. All right. So thanks a lot, everyone. In the next lecture, we'll be diving deep into the mathematics behind self-attention. In the lecture after that, we'll look at multi-head attention, and only then we'll be. So this is the multi-head attention notes, and only then we'll be truly ready to understand the key value cache. So let me see where that is. Yeah, only then we'll be truly ready to understand the key value cache, which serves as the segue for the multi-head latent attention, which is MLA. This series is going to be a bit deep, but I'm trying to make the lectures as long as possible so that I don't miss out anything. This is for serious learners, so please make notes as you are watching this series, and it will be incredibly useful for you. Thanks a lot, everyone, and I look forward to seeing you in the next lecture.